In a previous video, we saw how to calculate head losses in pipes using the universal formula. It was necessary to find the F value. We used the Moody diagram to find it. Another important parameter was necessary, the Reynolds number. It depends on the viscosity value, which is the matter of this video. Fluids, and consequently water, have an important property, the fluidity. They can easily change their shapes when submitted to shearing stresses. They can offer some resistance to this change, but no matter the intensity of F, a V will always occur. We can say that viscosity is the natural opposition to fluidity. Liquids with greater viscosity, such as honey and oil, have lower fluidity and consequently higher viscosity. In standard environmental situations, the viscosity of the liquids decreases with temperature. On the other hand, the viscosity of the gases increases with temperature. It's easy to understand what occurs in liquids. When the temperature increases, the intermolecular attraction effect decreases. Then, the liquid molecules can move easily between themselves. So, imaginary liquid slices can easily move inside it. See what happens with water viscosity. The higher the temperature, the lower the viscosity will be. But with the gases, the opposite happens. The higher the temperature, the higher the viscosity will be. See what happens with air viscosity. Why? Well, it's not so easy to understand. Air viscosity is related to the molecular exchanges between the two media that we wish to move. The greater the temperature, the greater this exchange will be. Let's try to make it better. Imagine rail cars standing side by side like this. One of them has a huge foam block over it, which can absorb a large amount of water. A water cannon is installed on the other one. Okay, now the cannon car is on the move. Nothing's gonna happen if the water cannon is turned off. But now it's working. Notice that it's transferring water to the foam block together with its momentum, so the foam car begins to move. And the greater the flow, the greater the foam car speed will be. Something like this occurs in gases. The greater the temperature, the greater the molecule exchange will be. And it will be more difficult to stop the foam car. Did you understand the analogy? Let me know in the comments. Very good. Now, returning to the subject of the video, the scientist that stated an equation for the viscosity was Newton. Yes, sir, the Sir Isaac Newton. Here we can see water between two parallel solid plates, shown in perspective and in transversal view. Here's the water between the plates. This one is a fixed plate and this one is a mobile plate. Let's apply a tangential force F on the upper plate. It will move with a constant velocity v. See what happens to the water. The particle that is near the mobile plate goes with it, and the particle that is near the fixed plate stays with it. We are assuming that there is a linear velocity profile, which means that the velocity variation is proportional to the distance. So we have v over y equals dv over dy. Velocity gradient is the name of this relationship. The relationship F over A equals tau is the shear stress. The relationship shear stress over velocity gradient is equal to mu, and it's called absolute viscosity or dynamic viscosity. The Newton's law of viscosity states that tau equals mu dv over dy. In this expression, tau is the shear stress, dv over dy is the velocity gradient, and mu is the absolute viscosity or dynamic viscosity. At 20 degrees Celsius, the water absolute viscosity is approximately equal to 10 to minus 3 pascals second. Kinematic viscosity is a measure of a fluid's internal resistance to flow under gravitational forces. Its expression is nu equals mu over rho. At 20 degrees Celsius, water kinematic viscosity is approximately equal to 10 to minus 6 squared meters per second. In this table, we can see how water viscosity varies with the temperature. It varies a lot. See what happens at 20 degrees Celsius. Mu equals 0.001029 pascals second, and mu equals 0.00001007 square meters per second. At 60 degrees Celsius, mu equals 0.000479 pascals second, and mu equals 0.00000478 square meters per second, less than half. And at 4 degrees Celsius, mu equals 0.001598 pascal seconds, and mu equals 0.00001567 square meters per second, more than 1.5 times bigger. See these tables. They show the water absolute and kinematic viscosity variation with temperature. These graphics show the same variation. As we know, water viscosity decreases when temperature goes up. Now, these two tables present the air absolute and kinematic viscosity variation with temperature. These graphics show the same variation. Note that air viscosity grows up when temperature grows up. It's interesting to note that the water kinematic viscosity at 20 degrees Celsius equals 10 to minus 6 square meters per second, and the air kinematic viscosity at the same temperature is 15 times 10 to minus 6 square meters per second. So, air kinematic viscosity is greater than water kinematic viscosity. That's why the cigarette smoke in closed environments rises without trembling. Greater viscosity decreases the Reynolds number, so the greater air viscosity brings to a lower Reynolds number and consequently to the laminar flow. Here he comes again, Mr. Reynolds! Yes, and I didn't forget my promise. We'll talk about him in my next video, I promise you. Yeah, I agree. Cigarettes are not good examples. Let's make an exception only to its smoke. But we can inject smoke from other sources in wind tunnels, and thus visualize the airflow around several geometric profiles, thanks to this air property. And yes, in our next video, we'll talk about the Reynolds number. Oh, and if you like this video, don't forget to give it a like, comment, share, and subscribe. Hit the bell so you can be notified of my next videos.